recall when we did factorization in the perturbative parts of this course, we divided up calculations of hard scattering processes into a parton-parton cross-section that was independent of the non-perturbative dynamics, which is a purely perturbative calculation. And then we stuck some PDFs on it to represent the probability densities of finding each of the incoming plane waves in the actual proton. Multiparton interactions just means doing that many times, naively speaking, that we can have the proton, we start decomposing it into having many partons. So we need something like multiparton PDFs, yanking several partons out. And for each one of them, if we start from perturbation theory, we would again calculate that there is some sort of perturbative scattering process at these PTs of 4 GeV. That's okay. Should be able to use perturbation theory to calculate the second one. As we go down to 2 GeV, 1 GeV, this starts to be more and more dubious. But certainly for the tail of these that have high PTs, it should be okay to use perturbation theory and to use a factorization ansatz of a similar kind as when we just use ordinary PDFs. But we will need multiparton PDFs. So in a Monte Carlo like Pythia, the way we construct these multiparton PDFs, which we don't get, yes? It will, yes. Yeah, that's a great question. I have not explained why there's a difference between minimum bias and underlying event yet. We will need to introduce one more component in order to understand that. So that will come, and if it doesn't, then remind me. So I'm just motivating that we would have multiparton interactions. They should be there in minimum bias as well. So we will still need to understand why are there more of them when I trigger on a hard jet than when I don't. So from PDFs, the normal PDFs that we use, they represent the partitioning of a proton into one parton and a remnant, and we don't care about the remnant. So we have the probability distribution of the parton, and the remnant is just inclusively summed over. But now we would like to have the partitioning of this remnant object into another parton and a remnant, and of that remnant into, so, you know, what are the, so there's obviously going to be some momentum sum rules to do with constructing these things. We cannot yank out more X than there is in the proton. And if we yank out a strange quark, then the remnant has to have an anti-strange in it. So there's sort of a pseudo valence, not really valence. We call it a companion quark. So you can construct, you can basically guess these multiparton PDFs using momentum conservation and flavor conservation to sort of at least have educated guesses for them, which goes beyond the existing factorization theorems. So now we can let this mechanism drive further color exchanges, and we can get more strings in hadron collisions, more hadrons. We could in principle also get additional lumpy structure in the event. There should be a tail where both of these scatterings are hard. I don't know if you've heard about double parton scattering could also be a source of double W production. 2 W pluses, double parton scattering should be a leading contribution to that you could make 2 quark-antiquark pairs annihilate 2 Ws here, things like that. So there's a bunch of interesting phenomenology associated with this. I will mostly just be interested in, you have a hard scattering that you're interested in, and then the underlying event is just additional QCD scatterings. But in principle, there is a small chance that you could have some other interesting physics process happening just by random chance. And so how many of them do you have? Well, we already looked at this ratio of the 2-to-2 partonic scattering cross-section to the total and said that that could be a gauge of roughly how many should you have to reconcile these two cross-sections. And the simplest thing you could do would be to say, okay, I'll use that as the mean of a Poisson distribution. It should just be a Poissonian randomly fluctuating thing where this should be the average that I should see. So I could just do a Poisson distribution with that number there. And that would be the basis of the first sort of very naive MPI model that you could build. In real life, of course, this cross-section should be damped at PT goes to 0. At some point, you cannot resolve color in the proton anymore. So you need a regulator for the perturbative scattering cross-sections there. And again, we talked about these are not all independent. There are global conservation numbers like momentum conservation. So that will kill the high end tail of the Poissonian, that at some point you cannot scatter out more momentum from the proton. And then what we need to discuss as well is impact parameter dependence. So how do these protons actually look? What does the mass distribution in the protons look? So in reality, it's not a simple process or product. There is non-Poissonian behavior, but you can build that in. And it's a nice sort of starting picture, at least, to think about that when these protons smack together, all of these parton interactions take equivalent snapshots of the other of each other, of the other proton structure. That everything happens very quickly, and at high Q squared, they're all sort of independent and they take equivalent snapshots. So there is an equivalent, a Poissonian structure there. It's just that there are, of course, correlations between them by global momentum conservation and flavor conservation. Pythia casts this whole thing, not as, we don't start from a Poissonian, but as an evolution equation. So in parton showers, you could also sort of say, well, I know that the splitting kernels are divergent, and so my X plus jet cross sections diverge. I can reconcile that with perturbation theory by doing parton showers, by saying that I have more than one emission on average. It's a very similar argument that you're making there. So here what we do is we cast multiparton interactions as a shower-style evolution. So we start at high PTs with the hardest scattering process. We use the normal PDFs for that. And then we evolve the entire event structure down with showers and multiparton interactions and everything else going on. So that's what I've illustrated here. You have the hard interaction that happens at the highest PT, then maybe it radiates, initial state radiation. Then at some other PT, you have a multiparton interaction that starts off another cascade and they evolve, and so on and so forth. So that's really how Pythia does it. I think it's still the only one that does interleaved evolution, if I remember correctly. Anyway, we were the first to do it. That was my PhD project, so I'm quite proud of this interleaving idea. So what that means is that initial state radiation and multiparton interactions compete for the X that's available in the remnant. So you've got some momentum reservoir, and you can either have an initial state radiation, move a parton to higher X, or you can scatter more X out of the proton. So there's an interplay between initial state radiation and multiparton interactions through this interleaving. And more recently, we've even included resonance decays in this whole interleaved evolution, where if you have a Z boson with a width of 2.5 GeV or so, when the evolution reaches a PT scale of 2.5 GeV, the Z boson disappears and is replaced by its decay products in this sort of overall evolution. And then at some point, you have color scheme. So that's the sort of physical picture of multiparton interactions and showers, and now resonance decays as well that we have. So now I want to get to impact parameter dependence, and that's what's going to generate the real difference between minimum bias and underlying event. So the simplest picture you could have, which nobody uses anymore, is just to take sort of gray or black disks, have the proton mass distribution be just disk-like, and then sometimes you have peripheral, sometimes you have central collisions. But you can even see in this picture here that sometimes when you have a central collision, you will tend to have many scatterings, and when you have peripheral collisions, you will tend to have not so many. So that will generate fluctuations. This multiplicity distribution that had these big fluctuations, this will generate an additional component that can fluctuate, that sometimes you have peripheral, sometimes you have central, so that's going to broaden out that distribution. You're introducing another fluctuating component. Another thing that you can sort of intuitively see is that when I have central collisions, I have a higher average number of multiparton interactions. That means I have n chances for a hard one. So any of those n can be a hard one, whereas when I have a peripheral one and I only have one, then I only have one chance to make a hard one. And that's going to give a trigger bias. When I trigger on hard jets, I'm going to bias my sample towards central collisions where I have more chances for one of them to be hard. And that's the crucial feature. So we interpret that as a kind of trigger bias. Now, what we do in reality is we use not just simple disks, but some assumed mass distribution that either follows the electromagnetic form factor of the proton that has been measured. So Herwig makes that ansatz, or simple parameterizations like Gaussians or something like that parameterizes the proton structure. It's not important to first order, at least, that you describe the exact proton structure, for instance, with 3 valence like bumps or something. You don't have to describe the detailed microscopic structure of the proton, but you have to sort of describe the fluctuations in overlap. So how peaky is the proton, whether it's distributed on 3 lumps or 1 lump, you don't really care that much to start with. Just, is it more or less peaky is really what you can see in the data, more or less lumpy. So you go between distributions that are more lumpy, less lumpy, Gaussian, double Gaussian, exponential, things like that. And then you can see what the consequences in data are. If you have a very peaked mass distribution, or you assume a very peaked one, then you're going to have big differences between central collisions and peripheral ones, because a lot of your mass is in this very narrow peak in the center of the proton, or the center of your parameterization. And when that happens to overlap, you're going to get a lot of multiparton interactions. Whereas when it doesn't overlap, you're going to get, so you have very wide fluctuations. You can kind of see how different mass distributions are going to leave an imprint on the fluctuations of these distributions that we're looking at, and on the difference between minimum bias and underlying event. So that constrains how peaky the distribution can be. So now, if we include sort of the disk-like proton, you already get a much more variable distribution just by the geometric overlap. But then when you also have, well, without variable impact parameter, that's just multiparton interactions with a constant, without variable impact parameter. When you then add variable impact parameter, that you can have these overlaps, and I'm not sure what mass distribution was used here, but you just see that you get this additional fluctuation from multiparton interactions, and then additionally from the variable impact parameter. And now you can get these big fluctuations and so forth. The jet pedestal also you can look at. Here they haven't really done it with a realistic Monte Carlo. They've just done without multiparton interactions. You don't have a pedestal. With multiparton interactions, but without B dependence, you still don't have enough fluctuation. You get a little bit of a pedestal, but not much. And then here you sort of increase the number of multiparton interactions artificially by 4. That's then a measure of how much you need your distribution to be peaked, but you need there to be sort of a factor 4 difference between central and peripheral collisions on average. So that is the additional physics that we think is going on, multiparton interactions and impact parameter dependent. And remember, this is just proton-proton collisions. We're not talking about heavy ion, where impact parameter, they talk about that a lot. This is just proton-proton, but there seems to still be an important effect of impact parameter that makes this difference between minimum bias and underlying events. So when we're looking at hard triggers, hard processes, we are looking at quite central proton-proton collisions. That's our interpretation. And so that's why there's additional activity in them compared to the minimum bias level. So how do we characterize the underlying event? I don't know if you've seen plots like this, but this is a sort of technique pioneered by Rick Field at the Peloton, where you look at a hard trigger object that can be the hardest track in the event, or the hardest track jet, or the hardest actual jet, or a Z boson, or some other hard trigger object. And then you look at right angles to that. So the jet should be going in this direction. There will, of course, by momentum conservation, be a recoiling jet in the opposite direction. But at right angles to it, you should be looking at not so much radiation, but more sort of the underlying activity. And so this gave a very simple observable definition. And then it can be up to models to see, can we populate that region correctly when you're looking at, so this is the azimuth in your detector, and you're going, you can still go forwards and backwards in rapidity. This is the azimuthal angle, looking at right angles to jets or hard trigger objects. So that's called the transverse region, and that is a useful operational definition for the underlying event. Now, once you start adding parton showers, then especially on the backward side here, you could have a radiation that would cause a 3-jet event, and some of that radiation will spill into at least one of these red regions. So often these 2 red regions are also divided into the transmin and the transmax, they're called, just based on which one has less and which one has more activity. The transmax is more sensitive to radiation spilling into that region, and the transmin is quite insensitive to radiation and really measures the underlying event level. So this is what it looks like. This is exactly the jet pedestal effect. This is what UA1 observed, now measured by Atlas. And you can see that as you trigger on a harder and harder leading track, going from just the smallest they can measure of around half a GeV up to tracks that would be associated with quite hard jets, you can see that you're going up in still looking at right angles to this hard track, you're going up in the activity in the transverse region. So this rise here is interpreted as increasingly biasing towards central impact parameters. And so the underlying event is rising up from minimum bias, which is down here somewhere, the average level. When you're not having a hard trigger at all, you're just triggering a sort of the average track anyway. And then you're triggering on progressively harder things, but at some point that saturates. You're central now. You can't get any more central than central. And then it flattens out. And then you have this underlying event plateau, which, as UA1 already concluded, is independent of the jet ET. So as soon as you have sort of, so this, what I call this is maximum bias instead of minimum bias. That's not a real word. Nobody talks about maximum bias, but it sort of is in a sense, right? You've triggered on a hard jet, and even if you trigger on a harder jet, it's not going to make the underlying event become any bigger than that. You can see that there is a small slope on this. So it's getting a little bit more busy. And I interpret that, and I think that is consistent with what we see when we study with models, that slight slope is due to radiation. So when you, of course, have harder and harder jets, yes, there will also be more parton shower radiation, soft radiation in your event. So it's not the underlying event that's coming up, it's radiation off your hard trigger object that's spilling into your transverse regions. So there should be a little rise on it. There is a little rise on it, but the underlying event has already been maximally biased.